Swayam Prabha. Digital India. Educated India.
Yes, so what we did is, we collected a few questions, mostly because the students can get chance to think and ahead of time and ask questions in this. So, if any student want to add more to what is already listed here, please jump in and then add. If you want to elaborate more on the questions, then please do that. The first questions, maybe I'll just read out the questions, and then any panel member then can start answering. So the first question is, what got you into this compiler design research? So maybe other panel members.
So Uday, the question goes to you first.
Okay. Okay. So what got me into compiler design was when I was doing MTech at Pune University. I had an excellent teacher by the name of S.N. Sapre. And the way he taught compilers, I got hooked to it. And I did my MTech project with him. We did something on incremental parser construction. So that's why I thought that I started liking the subject a lot. Of course, after that, I did my PhD with DMD at IIT Bombay. But S.N. Sapre, who now works at Intel, is my compiler teacher who got me into the area of compilers.
Yeah, thanks, Uday, sir, actually. So, would someone want to add more to this? Other panel members also, it would be interesting to know the answers from you as well.
Okay, let me just add something. I'm not yet into compiler research. People call me more of an architect rather than a compiler person. With that disclaimer, let me say that what got me interested in doing something compiler research is more from the point of view of, I look at computer systems as a whole, and computer architecture is what I understand slightly better. And I feel that there are lots of opportunities where with the combination of architecture and compiler, we could do actually better things. That's really what got me into compilers. Did a little bit of work on instruction scheduling, software pipelining, and related things. And some of my students taught me how to do more about data flow analysis, pointer analysis, and other things. I'm yet to catch up with them on those things. So that's really what my short answer to this question is.
Yeah, thank you, sir. So, other panel members?
If I may add.
Yeah, please.
This notion of how did you get into, I'll actually give a roundabout answer to it. Instead of saying, how did I get into it? I will say, how am I sticking to it? One may get into it in many ways, but when I teach compilers, right, there is one slide that I present in the beginning. It's one of those few subjects where pretty much every CS field gets impacted and impacts, starting from algorithms, architecture, OS, networking, DBMS, artificial intelligence, speak anything. And it's a space where there are excellent problems to solve. And I guess I'm kind of venturing into one of the future questions. This is something that it's going to be an evergreen field in the systems area, right? If computer systems have to survive, compilers have to survive, and it's an area which can which has problems. As long as CS is there, new hardware is there, new compilers are there. New language is there, new compilers are there. New compilers are there, you have new hardware and new languages. So it's a cycle. It's a beautiful cycle, and for every application, both domain specific and domain and general purpose, this can keep us give us bread and butter for a long time.
Yeah. Thank you. So I think that also brings us to the next question, where students were asking, when you're asking about the future of this particular compiler research itself, right? So the few questions, more or less, all are related to a similar thing, but I'll just read out the questions, then maybe from the keywords in the questions, then panel members can take forward the answer. So what is the biggest change in compilers you expect to see over the next decade? What should budding compilers researcher look out for? In the next few years, how do you feel the compilers would improve? And how do you believe systems will evolve in the future? Will applications drive the systems or systems drive the applications? I request the panel members to actually take the questions.
Yeah, so maybe I can add some color to this question. So not so much from a research perspective, but from a what I see as the trend in terms of the industry. I think that definitely there is, with this fourth industrial revolution and AI and everything, there is an entirely new class of applications that are emerging. And that's going to be very significant in terms of its breadth of impact. It's going to change every industry, every aspect of our life, whether it be, solving a complex problem like drug discovery or ordering a pizza for your dinner. So entirely new range of applications are emerging. And as a result of that trend, there will be new languages and new hardware, and ultimately a need for new compilers to meet that requirement. Okay, so I think that we are heading into a very exciting time going forward in the area of system design, which includes innovations in architecture, which includes innovation in compiler technology, which actually also includes innovation in language design and expressibility of programmer intent. And going back to the previous question, I would like to just add that my answer is very similar to what Ketkar sir gave, except just replace Professor Sapre's name with Ketkar sir's name. So, but in terms of what keeps me interested is compilers have this sort of unique capability. If you look at any software stack, it is perhaps only compilers as a software which is trying to decipher programmer intent. What did the programmer intend to do when they expressed themselves in this manner in the code? And how can I reverse engineer it? And how can I express it in a different way for some kind of a profit function? So I think that that's a very interesting problem at a high level. And of course, there are lots of interesting problems at low level. Many of them, you can say thankfully or frustratingly, are NP complete or NP hard. So we know that we are not going out of business anytime soon. So as long as we are challenged by some of the problems, we can keep sort of solving them for a new breed of applications that are coming up.
Yeah, thanks for the elaborate answer. Actually, that's helpful. Any other comments on this?
If I may speak, since DP has brought the earlier question, instead of answering what got you into compiler design, if that what is replaced by who, I would like to remember my professor and many of our Professor Preeti Shankar madam, who brought me into compilers, and it's a good time to remember them as well. I don't have anything else.
Thanks very much.
Let me add a few things to what Divyaprand said regarding compiler research.
Mm-hmm.
One of the things that I feel exciting is about this whole new area of domain-specific languages and newer target architectures, mapping these things to newer target architectures and things like that. That's one area where there is a lot of new activities that are going on. People are trying to make sure that we do this translation in a way which is very efficient and in a way where you could retain the programmer productivity and performance, right? They are very important. So that's something that is likely to happen. And this is going to be fueled by the fact that there are going to be newer and different kinds of hardware devices or accelerators that are going to come. And the applications are, as always, they are making more and more demands on the systems in terms of performance, and B, they are becoming broader and wider and things like that. So we are going to have newer applications. We are going to have newer, domains which are going to be looked at. We are going to have newer hardware that are going to come, and we need to kind of make sure that these things kind of together work well. I think that's one of the things that's going to be there. I'm sure that there are many other interesting, challenging problems in the space of compiler analysis. Perhaps Subhajit or Uday or even Krishna can talk more about that. I don't want us to just look at compiler only as optimization. There are also other angles to it. So,
just to add to what Govind sir said, so there are a couple of things. I think very soon the programs are going to look very different. So it's going to be sort of a combination of human written code that we right now see with a lot of machine generated code, maybe machine learning, like learned from machine learning models, maybe automatically synthesized code. And now how the compiler takes this weird program and optimizes it or translates it, or what can it do with it, it's going to be a very interesting thing to see. I think the other interesting challenge that we are going to see is the sort of the amalgamation of the traditional techniques, the conventional wisdom that we have learned over the last 50 years or so, and the new revolution that's coming in, like Dibapran said, this with machine learning and AI helping you out. And it's already happening. Like in compilers, we are trying to learn very interesting heuristics that humans could not have learned. We are doing, like, there is a lot of work going on in like changing the way what traditional compilers look like. But at the same time, there is a lot of conventional wisdom that we have learned over the last 50 years, and that's not going to go away. So the very interesting thing that we are going to see very soon is going to how these traditional techniques, sort of in combination with the modern tools that we get, combined together to get compilers which probably look very different than the compilers of today.
Yeah, thanks, Udit, actually. So, Uday sir, do you want to add something?
Yeah, I have already spent half an hour in the morning today on precisely this topic. I have given very elaborate answers and listed many things. So I will refrain from repeating anything. Krishna wants to say something, so let him go ahead.
Yeah, I mean, just to add this to the points of Govind and Shubhajit, right? I mean, you pick any program, right? I mean, there are so many things that we want to do, we as programmers. We want to run it all right. We want to analyze it, see if there are any bugs. We want to analyze it to find out how will it run, how much space will it take. We want to analyze it and say, hey, can it have deadlocks? Deadlocks if it is a parallel program. Maybe for some other program, we may want some other properties. So analyzing the code for performance, like Govind said, is just, I mean, it's one of the many things that can be done. And we are only scratching the surfaces at some level. I mean, we can analyze it for performance, we can analyze for safety, we can analyze it for program understanding, and each of these, depending, I mean, for a specific domain, for a specific target architecture, these things will keep on. I mean, it's an ever-expanding zone. I mean,
Yeah. Thanks for the answer. Actually, it's really encouraging to know about the future opportunities, even for the young people who are starting their research. Yeah. So that brings to the question which says about like how to pick a particular research problem, right? Actually, I'm hearing some echo, some noise. Yeah. So how to, I mean, especially for the young researchers, how do we pick a research problem, right? So, two questions in that line is, so I'm just reading out the question. Since so many optimizations have already been done, what could be potential areas of research apart from improving these optimizations? And oftentimes, as a graduate student in systems, it feels like all good ideas have already been implemented, and the rest remaining is the low-hanging fruit with no potential to create impact. How to overcome this? I think the previous answer already, I mean, partially answered this of the new opportunities, new research problems that are opening. But anyway, I think better to hear more from the panel members. Yeah. Over to you. Actually. So Govind sir, please start. Yeah.
Okay. So first, one quick comment is that I don't think people leave low-hanging fruit. Low-hanging fruits are always plucked. Okay, they were never left out. But it's, I mean, sometimes it's not a bad idea to go after the low-hanging fruits. But what, as a good researcher, one needs to do is that not just stop there, but go beyond that. That's really what is important. And it's oftentimes what happens is that you need to get started somewhere, and a low-hanging fruit is probably a good thing to start also. So that's not a bad thing, but don't stop there. That's my comment on that. Now, how do you find the problem? This is a systematic process. Actually, you need to read a lot about in the area in which you are interested, in which you want to pursue. You need to read a lot. And you need to understand what is happening. You need to know where the gaps are, and you probably need to do some kind of a motivation study to find out whether the kind of problems that you are looking at, whether there are enough opportunities for you to explore. So it's actually a systematic process. It's not like you come up with a solution for a problem. It's basically, you spend a lot more time trying to identify what the problem is, and then of course go about it in a very systematic way. It's actually a process. Research is a process. You need to learn the process, and if you learn the process the right way, the outcome will automatically happen.
So this is Ramakrishna. So the only point about the second, I just want to add a small thing to what Professor Govind said. What you call, till recently, LLVM was considered to be the pretty good infrastructure, and you have seen, we discussed a couple of hours back, MLR infrastructure only at the top level, but MLR infrastructure just was designed and what you call, and it is on the process. Pretty super exciting things are happening in MLR. So please, I don't think we should think that all good ideas have been implemented and they have been solved, etc. So MLR is one word answer to counter example to that particular point.
Yeah, thanks, Ramesh. Yeah.
So I think that the way I view it is the following. There are two categories of researchers. Some researchers are explorers and some researchers are cultivators. Explorers find out new lands, they will find new problems, they will solve a problem, and then they will move on to the next problem. Cultivators are the ones who look at the lands that have been explored before, but they give it laws and structure. So basically, research also requires not just exploration, but also new eyes. It's not just a new journey. You need new eyes to look at things. So even if we say many optimizations have been done, as the scale of the problem changes, many of the techniques become completely ineffective. So while you might say that you are improving these optimizations, but impact could be very significant, and it could require significant amount of intellectual challenge. Just take a simple example. Let's take some optimization, your favorite optimization, which is done by the compiler at the intra-procedural level. Just to take it to the inter-procedural level, it's a completely different ballgame. Now the optimization might still remain the same, but to do flow and context and field-sensitive analysis and answer the same questions at the inter-procedural level is a completely different ballgame. So I think there is a lot of work that could be done even for optimizations and analysis. And while There may be several low-hanging fruits. I'm sure there are many significant problems. For example, validation of optimizations. It's a significant problem. It has not been solved yet. Efficient interprocedural analysis. People have been trying for 20 years. There is no success. So there are several serious problems, not just low-hanging fruits, where very interesting research and I would say long-term research can be done. It's not something that you can do in 1 year or 2 years and finish it. I mean, several PhD students may have to work on it for several years to solve the problem.
Yeah, just to add to that, this notion, I really like this notion of, explorer and a cultivator. So I would say that if you are an explorer, then look at the areas where the, sort of baseline is changing. And what's your baseline? Your baseline is the architecture on which your generated program would run, or whatever is your target language, if that is changing rapidly. And if your applications or the content for which your compiler is really important is evolving rapidly. And both these sort of shifting landscapes can give rise to new problems to solve, right? As an example, when GPUs, of course, now GPUs are quite mainstream, but initially when GPUs sort of appeared, they had a very different approach to parallelism, where the compiler has to decide how many parallel threads have to run. And this is a very interesting problem, and I don't think that this problem has been studied in great detail to say that what is the optimal number of threads to run, given a fixed number of resources, decided entirely by compiler analysis. So there are lots of interesting problems to look at. It may be that there is this common belief that all the problems have been solved, all the heuristics have been designed, and there's nothing much more to do. But I think that it is the same vectors of change in terms of architecture and application, which is also going to give rise to new interesting compiler problems to solve. I think safety is yet another really good example, right? So now you see so many applications of robotics and self-driving cars. Each one of those have tremendous safety premium on it. How do you ensure that your compiler is safe? And as a compiler engineer or as a researcher, can you add value in really saving human lives? I think that's a great and not only a very noble endeavor, but also a technically really tough problem to solve. Yeah.
Thanks, Gurupran. So I just resonate with this second point. I really like it. And I think all graduate students, some point of the time, always feel like all good ideas have been done already. So how do I get a new problem? So I think there were some very good responses. So I'll just add one more thing to it, saying that a lot of ideas which have been evaluated in the yesteryears and probably have failed, sometimes some of them actually work today because the softwares have changed, the hardware has changed, and whatever we could not compute yesterday, we can compute it today. So there are many things, like for example, even AI, people have tried a lot of things in the 70s, 80s. It is, AI is not a very new idea. I mean, AI in the sense of like deep learning or artificial neural networks is not a very new idea. But now what we can do on today's systems, like with GPUs around, is something we could not have done yesterday. Even things like program synthesis, it was called program derivation, and it had been tried, and like there were like lot of papers in the 80s and all where people were trying to do program derivation. Sort of it did not really pick up that well, but now like it is a very it's a very common thing that people like try to like put in almost every system. So it is also important to evaluate ideas that have failed yesterday to see does it now work or not. So I think so that is another place you can start getting good research papers, because a lot of times we only try to keep on reading papers of like papers which are very recent papers, like last 5 years or so. But sometimes it is actually important to go back to the classic papers and read papers from the 60s and the 70s and the 80s, because there's some very, very good ideas sitting there.
Yeah. Krishna, sir, do you want to add something?
Okay, I wasn't planning, but sure, let's do that. I mean, there is one. The first point, since Shubha talked about the second one, I thought the first one may also be given some more. See, it's not, the goal is not just to improve these optimizations. When we study, see, there is a part where we study in the classes or in the summer school or anywhere. Right? We study what is already there, and we keep asking, how do you improve this, that? However, life of optimizations is much more beyond just improving existing ones. You can come up with new optimizations, and for that, that's a kind of a vast ocean, as we talked before. So let's not only be limited to either optimizations or only improving the existing ones. It's a vast space.
Actually, this answer is really, really useful. Actually, for everyone, I should say. I mean, it's nicely consolidated all the points actually to get how to go about finding research problems, how to see the existing things with new insights. I mean, go and reading back the old papers. It's really brought out really nice pointers for the young people. I think some of your fears might have gone by now. Really useful answers. Thank you. This brought to the, I mean, actually, I think Subhajit brought this point and the Vipran brought this point in the previous answers, is about machine learning, right? So there are quite a few questions on this. I'll just read out the related questions. Machine learning can implement for compiler design in supervised way. Can it implement? And which stages of compilation have the most potential for applying machine learning techniques? Would it help to try something language specific before the IR stage? And the third question is, would like to know more about the machine learning and compiler ongoing research. Yeah, I request students to, I mean, if at all the panel members are asking, and if you get some more questions on the answers itself, right, please jump in. It need not be one way. We just consulted the questions that you will get more time for answering questions, and we just clubbed all the questions. Please jump in and also interact with the panel members if you have anything to add or further questions on what they're answering now. So I request panel members to answer these questions related to ML and compilers together solving these problems too. Hello.
So
Let me answer it. Okay, go ahead.
Look, go ahead.
Okay, I wanted to answer it because I'm a person who doesn't do anything in machine learning, so I thought I'm uniquely placed to answer this. See, there are two interesting spaces here. I mean, the questions seem to be about how machine learning can impact compilers. So there is a very interesting keynote speech. It was given by the name. It was given in CGO 2020, I think. There are two aspects: ML for compilers, where you use ML techniques to improve compilation. Second, compilers for ML, where you use compiling for domain-specific ML things. Both are interesting. So, and you can use these two keywords, machine ML for compilers and compilers for ML. You'll find a lot of interesting things.
So, if I may add, like to the first point of what Krishna is talking about. So, there are two places where, I mean, other than many other things I'm sort of missing out on, but I'd like to really stress upon two things that ML has really impacted. One is that the compiler is full of a lot of heuristics. Like, for example, just give you an example, like loop unrolling is one heuristic, is driven by some sort of heuristic, which says that, let's say you're given a loop, how many times you can unroll the loop. And it's a very difficult thing to guess, because there are a lot of features which impact it. Like, for example, and people have some, like if you look at compilers like GCC, they have some really crazy heuristics going there. which probably look at a lot of things like the number of instructions in a loop, the register pressure, the nesting depth of the loop, maybe the branching depth of the loop, the call tree, like the depth in the call tree. So you can just think of any number of features which overall impact how many times you should unroll a loop. Now you can understand why it is important, because like if you unroll it 2 times, then the register pressure can increase, you can start like getting more cache misses. So the performance can deteriorate. But if you unroll it a good number of times, the compiler can really optimize the code better, because generally loop optimizations don't cross loop boundaries. Now, there have been a lot of work in figuring out this unroll factor, and people have used like machine learning to come up with interesting functions which can, given a set of features, which can tell you what is a good unroll factor. So there are like huge number of heuristics sitting inside a compiler, and machine learning is a very good way of learning such heuristics. Like these are completely black box techniques. I mean, you just do a lot of experiments, collect data, and try to learn a heuristic. Another very interesting area where compilers, machine learning has really impacted compilers is in testing compiler systems. Like I think Dibbabran mentioned about it, that I think Uday sir also talked about it. It's like when you have, like, let's say you have a compiler, and most often we think that a compiler does not have bugs. So you should go and look at the bug repository in a compiler like GCC or LLVM. I mean, you'll be scared. So now to find out if a compiler does or does not have bugs is a very difficult problem. And if you look at today's, like I think Dibbabran can vouch for that, but lot of companies, you will see a lot of positions for testing engineers who are about like figuring out if this particular compiler has bugs or not. What does it mean to have a bug? That it means that your program may be correct, the source code might be correct, but the compiler can generate code which is incorrect. So the output is not semantically equivalent to the input. So what machine learning has done is there have been some very, very interesting techniques of testing compilers. And especially there are like machine learning driven first testing techniques, which like create some very interesting programs, try to pass it through a compiler and try to see if it sort of crashes the compiler or produces results which are different. So these are, I think, just 2 things that come to my mind, which have really been impacted big way by ML algorithms.
Yeah, just to add to that, I think Subhajit, you brought out really good points. I think that in terms of heuristics, the way I see it is that compilers often deal with structural information about the program in terms of analyzing it, discovering certain patterns or certain constraints about what this input program means. But then it has to sort of search unbounded optimization space to discover what is the ultimate best or speed of light solution can I generate given this input. And it is in that searching that I think machine learning or AI or deep learning like techniques can be very useful, whether it be in terms of problems like register allocation or flow ordering of different passes, right? Or even things like say like in many cases we have just-in-time compilation, where compile time is a very important performance metric. So looking at the program, can I analyze and predict which kind of optimizations will be beneficial for this program? I think that's an excellent machine learning or AI problem or deep learning problem, which using patterns and using data can be effectively solved and plugged inside a compiler, rather than sort of doing it with structural information about the program. I think the point about bug fixing and discovering defects is very relevant. I think that's where, again, because the number of ways a compiler can be incorrect is so vast that it helps to use these techniques to search that space and to sort of navigate that tremendous number of combinatorial possibilities. So I think that there is a lot of use of ML inside compiler, but I also think that there is a lot of more opportunities in ML compilers for ML. So we are already seeing a trend of a lot of graph compilers. I think Ramakrishna pointed out about MLIR and a lot of other sort of upstream compiler stacks which are trying to assess machine learning and deep learning workloads and trying to optimize it. But there is also, I think, some research that will come out or is already happening about formalizing what is a ML program, right? And what are the semantics of it, and can a compiler really process that information rather than just looking at it data or as a data flow. Yeah, I'll let others also.
Yes, really nice points. Actually, I think many of you might have got the problems, the research problems also through this discussion, and some of the very new technologies have been brought into the discussion here. So, any students want to ask any questions related to this? Yeah.
Professor Kedkar raised his hand.
Yeah, please. Actually, I'm not able to see the other thing. I'm just seeing the slides. Ramakrishna, you can coordinate if someone.
Okay, thank you.
So Ramakrishna, you had raised hand, so you first go and then answer.
Okay, very nice points by Professor Krishna, Shubhajit, and Divya. I just have a couple of things to add. These deep learning channels, which are so pervasive nowadays, all these DNN, CNN, LSTM, etc., MaxPool, they are really they are polyhedral kernels. So there are a lot of techniques are being used. So that is one aspect which we should always remember, that obtaining performance on the new architectures is a compiler problem. It's so compilers are one more to repeat what Devada Krishna has said. Compilers are evergreen in this area. So if you have a new architecture and if you want to get the best performance out of it, you build a compiler. Please build a compiler using MLIR or one of the newer infrastructures. That's one point which I want to make. The other point is that with the advent of this deep learning and scalability of the various aspects of deep learning, whether it is straightforward DNNs or even reinforcement learning, etc., lot of very beautiful things have happened. Program similarity is right now a very important aspect. That classically it's an anticidable problem, but I think there was this Popple talk by Aaron Yahav, because that built from his quite an amount of research on code to wake and other areas, where you can actually take two programs and then tell how similar they are. It's like take two images, two cat images, and then tell a similarity, or take 2 digits and then tell how similar or dissimilar they are. In a similar manner, you can construct a program. You can take a program, you can construct a representation, whether it is at lexical analysis level, whether it is AST level, whether it is IR level, and then you can feed it in a nice manner. You can train it, and then you can actually use it for program similarity, and then classify the input programs, and then you can use it for various purposes, other purposes as well. So this is a very important area, and going forward, because there is a plethora of source codes in GitHub, and then many of them they are buggy, etc. You really want to build tools, and then program analysis, data flow analysis is evergreen here. You can actually take the program representation. Programs are not natural languages. You cannot use the same techniques which are built for natural languages and apply them to programs. You really wanted to build encode the AST in a nice manner. You really want to encode the IR in a nice manner. You want to encode the reaching definitions, etc., in a nice manner, in a powerful manner, so that you can do program similarity in a nice manner, in a reasonable manner. There will be false positives, of course. There will be and machine learning has its limitations, but these going forward will be applied, because as the user types, he or she wants a ML model to give him or her suggestions on the codes, and there are maybe 1,000 submissions also for every question in a university for any programming problem. You want to find out which are the obvious non-submissions. You want to throw them out using ML, and then for these you have to build ML models. And then the heart of it is program representations. This is one way in which compilers and ML can really work together, can make change in every programmer's life.
Okay, so let me also chip in a bit. Like Krishna, I would also like to claim that I'm miles away from ML. I do nothing about ML, and trust me, I'm very happy in life. One can be happy in life without doing anything about ML. I am an example of that. But as a compiler designer, as a researcher in compiler, what is my expectation of ML? What is the criteria where I will see, using which I will feel that yes, ML is useful in compilers? So there are two things. A, ML is very useful where we can have a cost-based comparison. So if there's a cost associated with an optimization, there's a cost associated with a certain code that we generate, and then ML gives me, okay, here is the least cost or here is the lesser cost, and then whatever techniques ML might use, if ML output can convince me that there's a lower cost and there's a better code, then ML will be useful. But everywhere we do not associate cost. Not everything that we do has a cost associated with it. Many things that we do has a cost associated with it. So that's one part of it. Second part of it, a major limitation of ML that I see as of now is the following. ML works like a black box. ML things are not explainable. So when ML gives you a result, as a compiler writer, I would like an explanation as to why this particular answer has been given, because I have to guarantee soundness. I have to guarantee correctness of a compiler. I can't simply say that, because this program said it's a cat, therefore it's a cat. I mean, I have to be able to assert that it's a cat and it actually is a cat. That is the job of a compiler. So until that explainability comes in, I think ML will have limited use. It will have use where human intervention can be built in. For example, Shubhaji talked about looking at bugs and searching through bugs, or even testing where you want to do randomized testing, where there will be some human sitting there and looking at what is the output of it and finally eventually saying, okay, this is okay. So that's where ML will be very successful. So that's what my opinion on ML in compilers is.
Thank you, sir. Thank you, Ramakrishna, also for sharing your experience. I think this is an important point. Maybe instead of saying that, ML can be used in compiler's perspective, but also we need to understand maybe where to use. Like, for example, as Shubhajit mentioned, exploring the optimization space or for testing, I think is still applicable. Maybe if we want to really talk about correctness, then I think, and soundness is important, I think we have to think about it. It's not, it's not, we cannot directly use ML topics, right? So students, students, other participants, do you want to ask anything on what is already discussed? Please, or shall I go ahead with the other questions? Of course, this is all your questions, but I thought you might be getting some other questions in between. Okay, then I'll just go ahead. So the similar, there are other questions in the same thing, mostly in the research in this space. So this question is about JIT compilation. Over the past 2 weeks, I have realized repeatedly that one of the biggest limitations in designing ahead of time compiler optimization is the lack of information at the compile time. Going ahead, what do you think is the value of focusing on more dynamic approaches like JIT compilation? Are there problem domains where it could have a decisive advantage? And these are independent questions, so maybe we should take one at a time. Yeah, Krishna sir, do you want to talk about this because you worked on JIT compilation?
I can. I'm sure there are others also who can give deep insights. When we say JIT compilation, there are things that we can do at JIT compilation that we cannot do at in regular compilation time. For a simple reason, during JIT compilation, I have lot more information about the input for which the program is going to run. However, as a result, of course, it has some serious advantages. However, it also comes with its baggage. There are optimizations that we can do at static compilation time that we don't do. It's not that it cannot be done, but we don't do at JIT time, because any analysis that we do at static compilation time does not get added. The analysis time does not get added to the execution time. On the other hand, the JIT compilation, any analysis we do, the analysis time is added to the execution. As a result, I have to be extremely careful about how powerful or how much time consuming the analysis is, right? So as a result, there are new analysis people are trying to design which will try to do things fast, may not give full 100% precision that we care for, but maybe 70%, 80%, somewhere there, but much, much faster. So there are problem domains where JIT compilation has advantage. There are problem domains which are specified for JIT compilation as well, right? So in the context of Java, in the context of C# and so on, and I guess nowadays there are also people are thinking about for doing something similar for JavaScript and Python and so on, where we want to have specific JIT specific analysis and optimization. It's a very interesting area. Thank you.
Thank you, sir. So others want to add on this?
Shubha has his hand raised.
Yeah, so just to add to Krishna, I think he has really given the pros and cons of JIT compilation. But one compromise between completely static compilation and doing a complete JIT compilation is somewhere in between, is to use something called PGOs, or profile guided optimizations. So the idea is that you run the program with some representative inputs and collect some information about it. So you have some idea of what is the sort of workload you have, or what are the sort of inputs that you are going to run your program with. And then you have all the time in the world to compile your program, because it is still offline. So you're still in the program, you're still not really, the compilation time does not get added to the runtime of the program. So that is sort of a compromise between doing a complete static compilation, where you do not have almost any information, and a complete JIT compilation where you exactly know the inputs you're running with, right? So you can have this compromise of using PGOs or profile guided optimizations. Again, this is a really big area. There is a lot of work on this, lot of papers on this, and I would really probably ask you to go ahead and even explore that particular possibility.
Yeah, I didn't want to add this because this is kind of very. I mean, we have done a fair amount of work on what we call as partial analysis, where we do the analysis static time, and we use the partial information. We cannot do complete analysis and then use it at runtime. Manas Thakur from IIT Mandi is an expert in that. But yeah, it's very exciting space of work where we do some part statically, some part JIT.
I'll go to the
just
next.
to add one point there, that there are certain specialized situations where JIT compilation is the only way to compile your shaders. So imagine a software system where you know what program to run or what that program will be based on user input as the user is using that software. So in some sense, the programs are constructed at the runtime of the application, particularly in 3D graphics, 3D rendering, film rendering. There are lots of areas in the media and entertainment. There are a lot of problems in which JIT compilation is the only way you can. There are no static compilers. Okay, and so JIT compilation is also very important in those segments. Yeah.
Yeah, thanks, Nidhi, for adding that. Yeah. So I'll just go with the next question in the interest of time. So are there ways to ensure data security on compiler level? Please, can you provide some resources? Anyone want to comment on this?
So I mentioned this in the morning. There's some work by Vijay De Silva on security aspects, but I don't know whether what exactly is the meaning of data security. By data security, if you mean the data should not be read by data of your program should not be read when your compiled program is running somewhere else. That's a different ball game. I don't know about it, but in general, optimizations and security conflict with each other, and there are some position papers on it, but I don't know anything about data security.
So Anupam, do you want to clarify your question here?
Yeah, so what Professor Uday said, exactly that was my question. If the space is not local, so it's running somewhere else, that's what I meant by that.
Okay, thanks Anupam. Yeah, so the next question is there any compiler that exists which consider target system, that's a cache or the memory hierarchy, to generate better program in terms of performance, since cache or memory hierarchy are not the same across systems? Govind sir, do you want to answer?
Yeah, he's an expert on this. So.
Yeah, I know that.
Okay, I have been waiting for this. Okay, good. At least people acknowledge me that I know a little bit on something. Okay, so again, these are techniques that have been talked about, how to optimize things for compilers. There are techniques that Ramakrishna again would be able to talk more about this. There are these cache miss equations which you can generate, based on which you can kind of suggest what transformations can be done. But of course, some of these transformations need to kind of work for the system in which you are running, because as you mentioned, the cache hierarchy could be different for different machines. So there are these configurable parameters that you can set, and then based on that, your compiler can compile. That is one option. There is also another area of research which probably does not come under compiler, but then what are called auto tuners, which essentially try to run different versions of the programs and then try to see what version works for different memory hierarchy and things like that. So in many cases, for example, a very, very classic example that people talk about is this computation of FFT. So there is an FFTW version which essentially tries to run this FFT program on your machine and then tries to identify the best version which could run, again using some auto-tuning techniques. Auto-tuning techniques are also applied for other kinds of optimizations as well. I cannot specifically think in terms of a particular compiler which has implemented this, but in general, many of the compiler transformations that people talk about do take into account some of these things and parameterize them, right? Ramakrishna, maybe you should be able to talk a little bit more about tailing and other things in this context.
Thank you, sir. So I don't have much to add other than the fact that cache miss equations can be calculated, for example, at least for polyidal programs, etc. But they are pretty complicated. They are what you have powers of 3, power 4, etc. polynomials, and then you can, once you characterize these polynomials, what you call these optimizing these polynomials becomes a pretty hard mathematical problem. And you don't want to just optimize these real polynomials. You want to optimize the interior points, and that becomes one more level of exponentiality. So this can be done, and there have been recent approaches. There have been very classic approaches on cache miss calculation, but recently also there have been some approaches on calculating cache misses very nicely. So it is possible to write a compiler using these cache miss equations. So we are progressing towards it, but more progress has to be done.